Hello students, in previous sessions we have completed the topic continuity and now we are entering into the topic differentiability. Okay, before entering into this differentiability topic, we need to recapitulate again the derivatives which we have studied in first PUC. Okay, so what we have studied in first PUC, we just check once. Okay, right. So we studied the topic derivatives in first PUC. So what are the things we have covered? If f is a real valued function, a be a point in the domain of f, then the derivative of fx at x equal to a is defined as f dash of a is equal to limit h tends to 0 f of a plus h minus f of a divided by h. Whenever the limit exists. Okay. So if that limit is not existing, we can't say that okay, this is the derivative of f at a. Okay, that's why we keep the condition whenever the limit exists. Okay, right. This is the definition we have studied. Derivative at a point. This one is derivative of f at a point x equal to a. Suppose just simply we want to write the derivative at some general point, derivative of f. Okay, the derivative of fx at any point of its domain is defined as f dash of x is equal to limit h tends to 0 f of x plus h minus fx divided by h whenever the limit exists. Okay, so this is at a particular point and this is at some general point of its domain. So f dash of x is limit h tends to 0 f of x plus h minus fx by h. Okay, so the name of this definition also called as first principle of derivatives. What we call it is first principle of derivatives. First principle of derivatives. Okay. So because from this all the derivative formula of functions we are going to define in this place. Okay. So these are the 2 points we have studied in first PUC, and based on this, with the help of these definitions, we have got the derivatives of some different functions. Okay. So we will just see that what are the things we have studied based on this. So this is the first principle of derivatives. F dash of x is limit h tends to 0 f of x plus h minus fx by H. Okay. So, by using this formula, we have derived some formulae. So, d by dx of or d by dx of sin x is cos x, d by dx of cos x is minus sin x, d by dx of tan x is secant square x, d by dx of cosecant x is minus cosecant x cot x, d by dx of secant x is secant x tan x, d by dx of cot x is minus cosecant square x, right. So, these are the trigonometric functions, its derivatives we found by using the help of this formula. Okay. So, and some other formula also we have got d by dx of x power n, which is n into x power n minus 1, and also we have studied some algebra of derivatives, d by dx of fx plus g of x is equal to d by dx of fx plus d by dx of g of x, d by dx of fx minus g of x is equal to d by dx of fx minus d by dx of g of x, d by dx of fx into g of x is equal to fx into d by dx of g of x plus g of x into d by dx of fx. This is also called as a product rule. Okay. And d by dx of fx by g of x, we can write it as g of x into d by dx of fx minus fx into d by dx of g of x divided by g of x whole square. Here always you have to remember one technique point. So, always denominator first you have to write here g of x, then you can avoid the mistakes what you are writing in that formula. Okay. And also we have studied apart from this d by dx of constant is 0, k is some constant. Okay. D by dx of constant is 0, and also we have studied particular cases of x power n. D by dx of x is 1, d by dx of 1 by x is minus 1 by x square, d by dx of root x is 1 by 2 root x. Okay. So, these are all the formulae we have covered in the first PUC only. Okay. So, we not studied anything now new. These are all the things you have studied in first PUC itself. Okay. We just recapitulated what are the things we covered in first PUC. Now, we go for the topic differentiability. Okay. So, right, differentiability will enter the topic. Just we have saw that what are the things we covered in first PUC, right. Now, so we are going for the differentiability. Here we are going to see the geometrical explanation of f dash of x for a particular case. I am just going to explain what this differentiability meaning is. Okay. So, the differentiability meaning is here the rate of change of one function with respect to the dependent variable. Suppose you are having a function like this, y is equal to fx we are having, y is equal to fx. It is a function, okay. X is a independent variable, y is dependent variable. Now, the rate of change of y, with respect to the variable x, we are going to see that. Okay. So, that rate of change we call it is differentiability. Okay. Rate of change of y with respect to x, the rate of change of y with respect to x. That means the rate of change of one parameter with respect to another parameter is called the differentiability or the derivative. Okay. So, the derivative always speaks of the rate of change of one parameter with respect to another parameter. Okay. So, that is the main thing. Whenever you see the word rate of change word, whenever you see, then there will be the involvement of the derivative. Okay. So, this rate of change is need in all sorts of sciences, even in social sciences also. Okay. So, if you go for economics, there also we need the rate of change of the price value and the stock. Okay. So, if you take the field of like space science, there also how the satellite is moving, at what speed it is moving, and if it move, then what distance it can cover. Okay. So, velocity distance relation. Okay. So, like that many examples we can see. Whatever we take the word rate of change, that means one parameter changes with respect to another parameter. Whenever it occurs, then the derivative will involve. Even in biological sciences also, the growth rate of bacteria. So, time and growth there. So, that okay, comparison between these two parameters. Wherever you get the rate of change, the word, definitely the derivative involvement will be there. Okay. It is one of the prominent topic we can say in mathematics. Because of this, the calculus is developed. Okay. It can connect it to in many areas, right. So, if y is equal to fx, then the derivative of y with respect to x, we write it as like this, dy by dx. The rate of change of y with respect to x, we write like this. Then dy by dx is the derivative of y with respect to x. Okay. In some places we denote dy by dx as y dash also. Dy by dx also we denote as y dash. Okay. So, dy by dx or y dash we used to write. If y is equal to fx, then also we can write, or f dash of x also we can write it. Okay. So, in three different ways you can denote the derivative of y is dy by dx or y dash or f dash of x, we can write in three different forms. Okay. So, from the first principle of derivatives, we got the formula like this: f dash of x is equal to limit h tends to 0 f of x plus h minus fx divided by h whenever the limit exists. Whenever the limit exists. Okay. So, now here also we need to think about it is a particular case of limit it is. It is a particular case of limit. A particular limit we are calling is a derivative of the function, right. So, whenever the concept limit comes, then we have to think again the left hand limit and right hand limit. Okay. So, if you want to say a function is differentiable at a point, then it should be the left hand derivative and right hand derivative both must exist and they must be equal, because it is nothing but a particular limit it is, right. So, if you want to say that a function is differentiable at x equal to a function fx is said to be differentiable at x equal to if the first point, if f dash of a minus, which is equal to limit h tends to 0 f of a minus h minus f of a divided by minus h exists. Second, f dash of a plus means limit h tends to 0 f of a plus h minus f of a divided by h exists, and these two must equal. F dash of a minus must be equal to f dash of a plus. Okay, a function fx is said to be differentiable at x equal to a if the left hand derivative at x equal to a exists, right hand derivative at a exists, and the f dash of a minus is equal to f dash of a plus. A minus, that means it is a left hand derivative. Here f dash of a plus, it is a right hand derivative at x equal to a. Here how we got this formulae, I will explain it to you. See that this is the first principle of derivatives. This one we are going to use every time, right. So, f dash of x is equal to limit h tends to 0 f of x plus h minus fx divided by h. This is the first principle of derivative. Suppose at a point we want, suppose at a point if you want to write that formula is f dash of a is equal to limit h tends to 0 f of a plus h minus f of a divided by h. It is at a particular point. Okay. So, and one more formula also we can write it derivative at a point as limit x tends to a fx minus f of a divided by x minus a. Okay. So, whenever we want the formula, the derivative at a point a means either you can use this formula or this formula, we can use it, either this or this. Now, how we got this formula? From here I just explain it to you. Okay. So, in this formula what I am doing is wherever a plus h is present now, in that place I take it as x. Okay. I take x is equal to a plus h. When I take x is equal to a plus h, then what is h become? H become x minus a, which implies h is equal to x minus a. And one more point, and when h is tending to 0, then x is tending to a definitely. Okay. Now, the same thing we are replacing here. See that limit, instead of h is tending to 0, what we wrote? X is tending to a, and wherever a plus h is present, I wrote x and f of a I kept as it is. In the place of h, I wrote x minus a. I hope you understand. From this formula, we have got this one, right. I just took x is equal to a plus h, then we got this formula f dash of a, we got it here. Limit x tends to a, fx minus f of a by x minus a. You can use this is a convenient formula to find out the derivative of a function at x equal to a. Now left hand derivative, if we go for left hand derivative, if we go for left hand derivative at point a, so f dash of a minus, so limit x tends to a minus fx minus f of a divided by x minus a. What I do now, in the place of x, I take x is equal to a minus h, because x is coming close to a from left. At the time the values are less than a, so less than a means, so just smaller than a. So for that purpose we take x is equal to a minus h, comma h is a small positive quantity, h is tending to 0. So what I write now, limit h tends to 0, I took x as a minus h now, minus f of a divided by, what do you get x minus a from here? Okay, so also we get x minus a is equal to minus h, no? Just we substitute minus h here. This is the formula I wrote here, you can check. Okay, limit h tends to 0, f of a minus h minus f of a by minus h, we got like that. And f dash of a plus, means limit x tends to a plus fx minus f of a by x minus a. Now here x is coming close to a, from right, that means the values are more than a. So it's more than a means I take x is equal to a plus h, h is a small positive quantity, tends to 0. So and also we get x minus a is equal to h from this. Okay, if I just replace these things here, what I get, limit h tends to 0, x is a plus h, so f of a plus h minus f of a divided by divided by x minus a means h. See that you just compare it, f dash of a plus is the formula how we got it. Okay, so these are all the formulas we have to remember it. Mainly you just remember these are the formulas. See, this is the first one, first principle of derivatives. The second formula at a particular point. Okay, so first one, this is the second one, and this is the third one. This is the third formula, means from here we got this one, right? And then you need to remember this formula also, f dash of a minus, this formula also, and f dash of a plus, this formula also you must remember. Okay, so this is the fourth one and this is the fifth one. Okay, so mainly you have to remember these 5 formulae. Okay, so that we can proceed further, right? A function fx is differentiable. A function fx is differentiable at x equal to a is continuous at x equal to a. Okay, a function fx is differentiable at x equal to a is continuous at x equal to a, but the converse is not true. But the converse is not true. What do you mean by that? Converse is not true means, okay, a differentiable function is continuous, but continuous function at a particular point need not be differentiable at x equal to a. Okay, right? So we are going to see the proof of this. Every differentiable function is continuous at that point, but the converse is need not be true. Proof of this. Suppose fx is differentiable. Suppose fx is differentiable at x equal to a. What do you mean by that? Fx is differentiable at x equal to a, meaning is f dash of a is equal to limit x tends to a fx minus f of a divided by x minus a exists. Right? This is the meaning of that. So we said that fx is differentiable at x equal to a. That means f dash of a is equal to limit x tends to a fx minus f of a by x minus a exists. Now we have to prove that this function is continuous at x equal to a. Now we have to prove fx is continuous. Fx is continuous at x equal to a. For that, what I do is I just consider limit x tends to a, fx minus f of a. We just consider this. Okay, limit x tends to a, fx minus f of a. Next step, limit x tends to a, fx minus f of a divided by, I multiply and divide with x minus a. I multiply and divide with x minus a here without loss of generality. I multiplied and divided with x minus a here. Now, by the algebra of limits, what I do is I apply this limit separately for this function and for this function. Limit x tends to a, fx minus f of a divided by x minus a into limit x tends to a into limit x tends to a x minus a we wrote. Now when x is coming close to a, the x minus a value will be 0. X minus a value will be 0. When x is coming close to a, at the time the difference also come close to 0 here. And what about this? It's a familiar format for us. It is a f dash of a. Okay. So here f dash of a exists in the sense it's a finite value. Remember that. Whenever we say the limit is existed, that means it's a finite value. Now what we can write from this? F dash of a into 0. What we can write? F dash of a into 0 we can write. So it becomes 0. What we have considered in this place, limit x tends to a, fx minus f of a we have considered, right? So and we got its value as 0, right? So limit x tends to a, fx minus f of a is equal to 0. So what we got now? Limit x tends to a, fx minus f of a, we got 0, right? We got this one. Now from this, by algebra of limits, what we can do by algebra of limits, we can apply again separately the limit for fx and f of a. So limit x tends to a, fx, limit x tends to a, fx minus limit x tends to a, f of a is equal to 0, right? So now limit extends to a, f of a. F of a means it's a fixed value it is. Okay, it won't change. It's a fixed value. That means it remains f of a only in this place. Right? So limit extends to a. What we got now? Limit extends to a fx minus f of a is equal to 0. So take this minus f of a to the other side. So limit extends to a fx is equal to f of a. What do you mean by that? That means the function is continuous at x equal to a. Therefore, what I can say, therefore, the function fx is continuous at x equal to a. Right? See that the limiting value of the function at x equal to a is equal to the function value at a. So that's why we can conclude that the function fx is continuous at x equal to a. What we have considered and what we have got now. So what we considered that fx is differentiable at x equal to a. What we considered, fx is differentiable at x equal to a. We considered and we were able to prove that fx is continuous at x equal to a. Right? So the converse is not true. Converse is not true. Okay. So for that we will give one counter example. Okay, where a function is continuous but not differentiable. Okay. So see that now converse is not true. Right? Consider a function fx is equal to mod x. Consider a function fx is equal to mod x. Okay. Now we'll see, we'll discuss at x equal to 0 its continuity and differentiability. Both we'll discuss. Okay. Discuss continuity at x equal to 0. At 0 we were working now. So fx is equal to mod x, meaning is minus x if x is less than or equal to 0, plus x if x is more than 0. Right? So this is the mod function definition. At x equal to 0 we were working now. Because the function is splitting at 0, so we need to work it out, left hand limit and as well as right hand limit. Right? So f of 0, first f of 0 is mod 0 is 0 only. Right? Now LHL will work it out, left hand limit. Limit x tends to 0 minus fx. Means x is approaching to 0 from left. At the time the function is you have to take x less than 0 minus x minus 0, 0 it is. And right hand limit, limit x tends to 0 plus fx. So limit x tends to 0. 0 plus means x is approaching to 0 from right side. So mod x become x. It is 0 only. So left hand limit is same as right hand limit. So limit is existed here. Limit x tends to 0 minus fx is equal to limit x tends to 0 plus fx is equal to 0. So therefore limit x tends to 0, fx is equal to f of 0. Right? Because f of 0 is 0, we got it. So that means what we can conclude now? What we can conclude? So fx is continuous. Fx is continuous at x equal to 0. Now we will discuss for the same function differentiability at x equal to 0. We will discuss differentiability at x equal to 0. We will discuss differentiability okay. So we will discuss differentiability at x equal to 0. So we will discuss left hand derivative. Left hand derivative. Okay. F dash of 0 minus. F dash of 0 minus. What is the formula we have? Limit x tends to 0 minus fx minus f of 0 divided by x minus 0. So, always remember this formula, f dash of a is what? Limit x tends to a, fx minus f of a divided by x minus a. This is the formula we are applying now. Fx minus f of 0 by x minus 0. So, x is approaching to 0 from left. That means x is less than 0. When x is less than 0, what function you have to take it? Minus x you have to take it. When x is less than 0, you have to take the function minus x, right. So, limit x tends to 0, limit x is 0, fx you have to take minus x minus f of 0 value is 0 divided by x minus 0. So, what we are getting here? Limit x tends to 0 minus x by x. So, limit x tends to 0 minus 1. That means limit of a constant is constant minus 1, we got it. And the same way we will find out right hand derivative also. Okay. RHD, right hand derivative, f dash of 0 plus limit x tends to 0 plus fx minus f of 0 divided by x minus 0. So, limit x tends to 0 plus, that means x is approaching to 0 from right, that means x values are more than 0. When x is more than 0, the function you have to take it as x, right. When x is approaching 0 from right side, that means the x values are more than 0, you have to take the function x here. So, x minus f of 0 value is 0 divided by x minus 0. So, what we are getting? Limit x tends to 0, x by x. So, limit x tends to 0, we are getting 1. So, that means this value is what now? It is 1. So, you can observe clearly, left hand derivative we got minus 1, right hand derivative we got plus 1. It means f dash of 0 minus is not same as f dash of 0 plus, right. That means what we can write now, therefore, fx is not a differentiable, not differentiable at x equal to 0. So, what do you observe now? It is continuous, fx is continuous at x equal to 0, fx is continuous at x equal to 0, but not differentiable at x equal to 0, we have proved, right. So, what is our final conclusion? Hence a continuous function at x equal to a need not be differentiable at x equal to a, right. So, it is one of the important theorem for 5 marks. Okay. So, we saw that what a differentiable function is continuous, but a continuous function need not be differentiable, right. So, one of the very important theorem this is. So, we have completed one important theorem. So, whenever a function is differentiable, then it is continuous, and the continuous function need not be differentiable, we saw. And now we will see a problem here. Prove that the function f given by fx is equal to mod x minus 1, x belongs to R, is not differentiable at x equal to 1. Okay. So, if you see the solution for this problem, what they have given fx is equal to mod x minus 1. By the definition of mod x, what we can write this is, it is a minus of x minus 1 if x minus 1 is less than or equal to 0. Just it is x minus 1 if x minus 1 is greater than 0, right. So, by the definition of mod x, you all know that mod x definition. Mod x is minus x if x is less than or equal to 0, x if x is more than 0. In the place of x here, x minus 1 is present. So, which is equal to minus of x minus 1 if x is less than or equal to 1. Just minus 1, take it to the other side, you are getting plus 1. And x minus 1 if x is more than 1. Okay. Now, we work it out the derivative at x equal to 1. Before that, we take f of 1 value. What is f of 1? Mod 1 minus 1. So, mod 0, you are getting 0. Now, we start work on left hand derivative. So, LHD, left hand derivative, f dash of 1 minus, it is limit x tends to 1 minus f of x minus f of a divided by x minus a. Here a is 1. Always remember the formula, derivative at a point, f dash of a is equal to limit x tends to a fx minus f of a divided by x minus a. This formula, always remember it, right. Now, I use that formula. So, what I got, limit x tends to 1, 1 minus, that means x is approaching to 1 from left. That means here x is less than or equal to 1. What function I had to use? Minus of x minus 1 I have to use it. Minus of x minus 1 minus f of 1 value we got 0 divided by x minus 1. So, limit x tends to 1, limit x tends to 1 minus of x minus 1 divided by x minus 1. X minus 1 get cancels, you are getting minus 1. So, limit x tends to 1 minus 1. So, limit of a constant is again constant here minus 1. And the same way we work it out, right hand derivative also, RHD, f dash of 1 plus. So, limit x tends to 1 plus fx minus f of 1 divided by x minus 1. So, x tends to 1 from right. That means the values will be more than 1. The values will be more than 1 here, 1 plus. That means you are approaching to 1 from right side. That means the values are more than 1. When x is more than 1, what function I have to take it? X minus 1 I have to take it when x is more than 1. So, we substitute now in the place of fx as x minus 1. And f of 1 value, what we are having? 0 divided by x minus 1. So, what we are getting? Limit x tends to 1, limit x tends to 1, x minus 1 by x minus 1, x minus 1 by x minus 1. Both get cancels, you are getting 1 here. So, limit x tends to 1 you are getting. Okay. So, that means limit of a constant is again constant. So, see that left hand derivative you got minus 1 and right hand derivative we got plus 1. So, left hand derivative is not same as right hand derivative. F dash of 1 minus is not equal to f dash of 1 plus. So, we will write f dash of 1 minus is not equal to f dash of 1 plus. Therefore, fx is not differentiable at x equal to 1. Okay. Hence proved. That is what now they asked, prove that the function f given by fx is equal to mod x minus 1, x belongs to R is not differentiable at x equal to 1. So, we proved that it is not differentiable at x equal to 1. Prove that the greatest integer function, the greatest integer function defined by fx is equal to, okay, box x, 0 less than x less than 3 is not differentiable, is not differentiable at x equal to 2, is not differentiable at x equal to 2. We see this problem, right? Fx is equal to box x, okay, greatest integer less than or equal to x, right? Box x gives what? It's the greatest integer less than or equal to x. So here they mention 0 less than x less than 3. So up to that extent they have defined this is 0 less than x less than 3. Okay. So now what I do is I just split this function, okay, based on its definition. So 0 to 1, when x is lie from 0 to 1, box x value you all know it, it's a 0 it is. And when x is lie between 1 to 2, the box x value is 1 it is. And when x is lie between 2 and 3, the box x value is 2. Okay. Once you split this function like this, then automatically you can solve the problem very easily, right? Now we will work it out at 2, no, they asked at x equal to 2. So what is f of 2 value? Box 2, it is 2, let it be. Now we will work it out left hand derivative, LHD, okay, left hand derivative, f dash of 2 minus, f dash of 2 minus. So limit extends to 2 minus fx minus f of 2 divided by x minus 2, because we have the formula f dash of a is limit extends to a, fx minus f of a by x minus a. That formula I used. So limit extends to 2 minus, that means x is approaching to 2 from left, that means x is less than 2. So what function I had to use? 1 I had to use it. So 1 minus f of 2 value, we have 2 divided by x minus 2. So what we are getting here? What we are getting? So limit extends to 2, 1 minus 2, that means minus 1 divided by x minus 2. When x is coming close to 2, x minus 2 tends to 0, right? When x is coming close to x minus 2 tends to 0, minus 1 by 0. So that means minus infinity it is, minus infinity. Okay. So when x is coming close to 2 from left side, at the time the derivative you are getting minus infinity. If you go for right hand derivative, RHD, f dash of 2 plus, which is equal to limit extends to 2 plus fx minus f of 2 divided by x minus 2. So limit extends to 2 plus, that means x is approaching to 2 from right side. At the time x value will be more than 2, you have to take the function 2 here. So fx is 2 minus 2 divided by x minus 2. So limit extends to 2, you are getting 0 by x minus 2. So limit extends to 2, 0 it is. It's a constant. So limit of a constant is constant, 0 we got it. That means the right hand derivative we got 0 and left hand derivative we got minus infinity. Okay. So limit is not defined now. Okay. So that means left hand derivative is minus infinity and right hand derivative you got 0. So that's why what we can say. So the function is not differentiable at x equal to 2. Okay. We'll mention here left hand derivative f dash of 2 minus does not exist. Okay. Hence fx is not differentiable at x equal to 2. Okay. So I think you have understand the differentiability, how we can do it for a function at some particular points. Okay. So, thank you students.